Hi, everyone. We have so much to go over today. I know I say that like every week, and every week it's true, although this feels like the worst in terms of the amount and complexity of what we'll be talking about. So, I am going to put my usual disclaimer at the beginning, which is that like I'm trying to condense multiple master's or doctoral level course content into one sub 1 hour lecture. So I'm basically going to introduce a lot of words, concepts, ideas, and like barely scratch the surface of them. And the slides will be posted and this video will be posted and you can go back and rewatch them. As always, there will be some resources on the last slide. And then I encourage you to reach out to me or to others as you're kind of thinking about analysis. There were two learning objectives set for today. And it turns out I'm only going to work on the first one because just doing that in an hour is already too ambitious. And we're going to push the data visualization piece to a bit later. So today we'll just be talking about study design and quantitative data and sort of some fundamentals of quantitative analysis. I wanted to just throw up a couple of like quick visualizations for you that I thought could be really helpful. Both of these are from this great open source EPI website from a faculty member in Canada. And this is an overall classification of study designs, which I thought might be really helpful. It also introduces some vocabulary that I've mentioned, but also things I haven't mentioned. So I liked this kind of flow chart for thinking about what type of study you might be undertaking and how it fits into the kind of architecture or like some kind of a taxonomy of other study designs. So I just wanted to show this quickly. And, I think we talked in the beginning part of this class a few weeks ago about, differences between experimental and observational studies. And so just being sort of conscious of what you're doing and the pros and cons of the different design, I think is really important. So I thought this might be helpful. And then I also wanted to give a quick shout out to like EPI studies because I really haven't touched on those. The presentation I gave was much more focused on evaluation designs, but there's lots of different designs in epidemiology, basically looking at measuring exposures and outcomes and sometimes the relationships between those. And so I also wanted to put this slide up because these may be terms that you hear as you're thinking about your own work or reading papers. And so I thought it might just be helpful for you to have a sort of point of reference for understanding, sort of what some of these designs are doing in broad strokes and how they relate to other designs. So I'm not really going to talk about these very much, but just so that they're there, you have the source for them and you can go back and read more later. Okay, so the first thing that I want to say about our conversation today, as you're thinking about analysis, is that I am a big stickler on this, that I think the most important thing is that you have clear research questions up front. And, everything else basically flows from this. So let's just say that we surveyed each of you after every lecture that I gave. What research questions could we answer with those data? This is like open to free response. So just unmute yourself and shout things out.
I think like qualitatively, like how we felt about the structure of it, like if we felt like it was a lot of material or not a lot of material. And then also you could kind of survey us before like what we learned and then after, or what we knew and then after what we learned, and to see if we like actually retained the information.
Great. So we could do a kind of knowledge assessment, right? So let's take just that one to start with. So the research question might be, are these mini lectures resulting in increased knowledge on the topics covered among students who attend, right? So a sort of something that ends in a question mark. And that would be a different research question than, are students satisfied with the scope of topics covered during these mini lectures? Great. What other questions could I ask if I were doing surveys on you every week or whatever? Don't be shy. I'll sit here for forever.
You could also assess like what background we have in this and kind of compare that to what we've been able to learn, like put that within what did we learn and then what was our background before to see if there's any like intersection with that.
Great. Would you like to rephrase that as a research question that ends in a question mark?
I would love to. The thing, like, do students with a previous background and research experience or like statistics courses, or are they more likely to like obtain the information taught in these lectures?
Great. Thank you. Just one more. Someone give me one more research question I could ask if I were surveying you after every lecture.
Did students who are beginning qualitative analyses in global health projects find like X or Y training helpful toward their project?
Great. Yeah. So something about sort of utility of these lectures, and that would be a totally different question than knowledge or was the scope correct, right? So these are all completely different questions. You would go about them in very different ways. And you can tell even from the structure of the questions what we're interested in answering. And so this is why I'm such a stickler on sort of research questions up front, because it really helps to have an idea of what you're asking. And from that, your analytic approach flows. If you've done it truly at the beginning, your data collection flows from there. So everything flows from your question. So like, you know, are we talking about a how much question or a who question or a why question, right? These are all different kind of like question words or however you learn them when you're a kid. And those like will absolutely shape how you're designing your study, who you're talking to, who you're comparing, how you're going to analyze and present your results. So like really thinking this through, you know, am I interested in like how much everyone got out of each lecture, or just was it an overall net gain, or who got the most, or, you know, those are all different questions and will require slightly different study designs and analysis approaches. As one of the reasons there's two reasons I really like stating research questions as research questions. The first is that the question word is very important. And the second is that as you're articulating a question in the form of a question, an outcome sort of pops up, because essentially the structure of a question phrase forces you to say what the outcome you're looking at is. And so in the process of formulating your questions, you'll be forced to think about the outcome. As you're thinking about the outcome and you're planning your design and thinking about analysis, one thing you have to think about are the relationships between variables in the hypothesized world that you're looking at. And I'm very sorry because the slide is really dense, but we're just going to go through it sort of type by type. So this is like the most ideal, simple, straightforward relationship. There is an outcome variable, also known as a dependent variable, and that is directly influenced by an independent, also known as exposure variable. So there's some exposure, there's some outcome, there's a clear one-directional linear relationship between the two. This is what randomized controlled trials emulate, so that there's an exposure, you know, a medicine, a vaccine, whatever, and there's an outcome we're looking for. This is what an RCT does. There are some examples where we have this really straightforward relationship between an exposure and an outcome that are not RCTs. So like, you know, one sort of straightforward one is asbestos exposure and risk of mesothelioma, but like not every, you know, if my dependent variable here were like risk of lung cancer, it would be very hard for me to build that direct of a causal model between an exposure and that outcome. So this is like the ideal scenario because it's very clear, but it's very rare. So this is like a beautiful, simple model to start with, but you need to be realistic about the fact that you will see this very rarely. More common are models that include mediators or moderators. And so I'm just going to talk about both of them because these affect your study design. So mediators essentially represent alternative pathways between your independent and dependent variables. So there is a relationship here between your independent and dependent variable, but there's also a pathway that goes through some other variable. And so the total effect of, sorry, there's a typo here, of your independent variable on your dependent variable constitutes that direct effect, that horizontal line, as well as that indirect effect that's operating through the mediator. So this is important because if there is a mediator in the relationship between your independent and dependent variables, but you haven't measured it and all you've measured are your independent and dependent variables, you're only going to observe part of that relationship. You're going to miss the entire pathway that operates through your mediator. So really thinking about your question and your conceptual framework is helpful for being like, oh, wait, there's another pathway here. And we need to measure some of this mediation in order to capture the true relationship between the independent and dependent variables. So it's tricky to come up with good examples of mediators that are clean, but here's one. So, you could argue that one's job performance is influenced by job incentives, right? If you're offered a bonus or you're offered some kind of job-based incentive that may increase or improve your job performance directly. However, those incentives may also increase your job satisfaction. You may be happier at work, you may like coming to work more, you sort of are just generally happier, and that in turn would also influence your job performance. If we didn't measure job satisfaction and we just measured, your kind of bonus payments and your job performance, we would be missing out on that whole other pathway. So this is an example where sort of really thinking through these factors, these variables, and these relationships is really important. So that's mediators. Hopefully that makes sense. The other major type of variable you can think about are moderators. So moderators don't necessarily have a direct relationship in the same way between the independent and dependent variable, but they impact the relationship between the independent and dependent variable. So they're not another pathway, but they change the relationship between these two variables. Another word for these is effect modifiers, if you've heard that term. And what it really means is the relationship between exposure and outcome is not the same for everyone. There's some other factor that changes the nature, the magnitude of this horizontal arrow. So again, this is something you have to really think through, because if you think that there is a moderator, but you're just looking at everyone all together, you're not going to observe the heterogeneous effect, right? So if something has an overall positive effect for one group, but a countervailing negative effect for the other, it might wash out at the population level. Whereas if you had looked at those groups separately, you would get to observe those two different relationships. So moderators are really sitting sort of on this relationship between independent and dependent variable. And this is a really classic example of a modifier, an effect modifier or moderator. So work experience impacts the salary that one makes, but we know that that effect is modified by gender. So women see a different relationship between work experience and salary than men do. So if we didn't stratify our analysis by gender, if we didn't take gender into account and we just looked at everyone all together, we would be missing some of the nuanced relationship that exists, and actually the effect would be attenuated probably in this case because the female worker effect would not be included. So again, really thinking hard about the variables, your outcome, what you think your independent exposure variables are, and other pathways and other variables that may be affecting those relationships. This is a key part of thinking about your study design and setting up your analysis. I wanted to say a quick note on confounding just while we're on this topic. Confounding is a term that you're probably going to hear all the time if you do research work. People are very concerned about confounding because it affects your ability to draw inferences from the relationships that you're seeing. What it does is confounding variables affect both the independent and dependent variable, thereby creating a spurious association between those. And so I'm going to show you an example. So one is warm weather has a positive association with ice cream sales. When it's warm out, more ice cream is sold. Also, when it's warm out, more people go to the beach and there are more shark attacks, okay? If we did not think about the warm weather effect and we just measured ice cream sales and shark attacks, it would appear as though there is a positive correlation between ice cream sales and shark attacks. Like there's something about people buying ice cream that makes sharks attack them. that's not true. This relationship is confounded by warm weather. But if we haven't thought this out and thought that through, we're going to see this spurious association between those two variables. So I like this example because it's just like so kind of like ludicrous, but you can imagine times when it's really tricky to identify those confounding variables, and it requires really careful thought. Are these two things, is this truly a relationship that we expect to see, or is there something else that's driving what we think is an association? So all of this, thinking about confounding, thinking about moderators and mediators, are things that you should be doing upfront as you're kind of writing your research question, articulating your outcomes, and thinking about measurement, because you want to make sure that these other constructs are making it into your study design so that you're measuring them and capturing them. So your job as a researcher is to be specific, thoughtful, and clear from the very beginning about your research question or research questions, how those translate into a robust study design, and then what you're measuring as what type of variable. What's your outcome? What's your exposure? What's a potential mediator? What's a potential moderator? Are there any confounders? So really thinking that through from the beginning so that everything else can flow accordingly. This might sound really daunting, and it is. I mean, this is a really hard part of study design. I have two recommendations here. So first is, theoretical frameworks and existing conceptual models can help you enormously in specifying this. So, everyone here will be doing innovative new research, but chances are there is someone else who's looked at something maybe similar, like on a different outcome, different population or something, but you could learn. You can look at their model, you can look at what they've done, and that may help you think about these different variables and how they relate to one another. So use existing frameworks, use existing models. They're really valuable. Oops. And talk a lot. Talk to your collaborators, talk with experts in the field, really talk to people who know this material and can help you think about the variables and their relationships to one another. And this will be specific to your research topic and your research area. Okay, so just a quick note on research questions. I've already plugged they should end in a question mark, and I just want to sort of talk through a couple examples of kind of getting to better research questions. So, if you told me you were interested in understanding the patient population at hospital ABC, I would say, okay, that's not exactly a research question. Can we do better? So better would be who is coming to hospital ABC? Okay, slightly better. And now I understand it's a who question. Even better than that would be like, what is the age distribution of people with scheduled outpatient appointments at hospital ABC during January of 2020? So I've now like honed in really tight on not just who, but what's the attribute of the who that I care about, not just coming to the hospital, but I want to know this specific service line or this specific department, and I want to know this specific date, right? So I now, from here, have a level of specificity from which I can start to design a survey, a data collection tool, and a study. So really kind of narrowing, specifying, and getting really detailed and precise on what you're interested in. I do just want to note that like this research question is a different research question than what is the average age of people with scheduled outpatient appointments, or what's the age distribution of people who attended outpatient appointments versus scheduled, right? So every word that made it into this research question was meaningful in terms of how my variables were defined and how I would measure them. And it's not that one's better or worse than another. It just depends what you're interested in knowing. Here's another example. So this starts as a question: how diverse is the patient population in hospital ABC? I would say, okay, that's all right, but can we get more specific? So better than that might be, how many Latino patients come into hospital ABC? Okay, but better than that would be, what percentage of adults attending outpatient appointments at hospital ABC during January 2020 identify as Latino? I just want to point out that that's, again, a different question than what is the number of adults attending outpatient appointments. And you might want to think about sort of what do we learn from looking at a number versus looking at a percentage? Sort of what lessons do we take away from looking at quantities versus shares? And again, not that one is better than the other, but they just tell you different things and you learn different things. So a quick thing on like, what doesn't this tell us? So it doesn't tell us like how many Spanish-speaking staff we need. In order to know that, we would need to know patient language preferences. It doesn't tell us like how many additional Spanish-speaking staff do we need, what types and what service lines. We would need to know our current staff and their language proficiency. It doesn't tell us what care-seeking barriers do our Latino patients face. That would require additional information about care-seeking patterns and also probably qualitative data. So again, that's okay that it doesn't tell us these things, but you should just be cognizant of what scope your research question is taking and what you're not answering and what you will be able to answer, and maybe think about if you have to change your study design and maybe to expand your research question in order to answer what you're really interested in. Okay. So part 2 of this lecture is like, all right, let's just say, okay, you've set everything up really well. You have a clear research question or set of research questions. You thought about your outcome variables, whether it's confounded, and you're measuring all the mediators, and you've kind of done all of that. Now what? So you remember last time we talked about different types of data: dichotomous, nominal, ordinal, continuous. And we're going to talk about kind of what you can do with those different data types, because those different data types correspond to different types of analyses. Again, I'm going to try to condense like many statistics classes into a really short presentation. So, you know, if you have questions or whatever, we can always talk about them offline. I do want to just flag that there's tons of really nice flowcharts out there to help guide you towards what analysis might be right for you. And these are just a couple examples. If you Google, like, you know, choosing a study design or choosing a method, you'll find tons of these flowcharts. There's lots and lots and lots of them of varying levels of complexity, and they can be really helpful. So just, again, to flag that as a resource for the future. I'm going to talk kind of in like broader strokes than that, just so you have a sense of like categories and options. So there's many types of analyses, but I'm mostly going to talk about inferential versus descriptive or comparative. So descriptive and comparative have to do with the sample that you've observed. Inferential statistics, inferential analyses, are where you use data from your sample to infer something about a bigger population. So descriptive is exactly as it sounds. It is describing what you've seen. It's painting a picture of what you've observed in the sample that you have. Inferential is making inference. It's saying, okay, I looked at this sample, but I want to say blah, blah, blah about a population beyond who I've looked at. We'll talk more about this in the next half hour, but just like as a quick way to tell what's what, anytime you see a p-value or a confidence interval, that's an inferential analysis. So anytime you see anything to do with p-values, confidence intervals, asterisks, levels of significance, whatever, that's inference. Yeah, that's sort of like Cliff's notes on how you might be able to differentiate between when someone is presenting a descriptive versus an inferential statistic. So descriptive statistics, using data to show or summarize characteristics of your sample. Inferential statistics, using data from that sample to make predictions about characteristics of a population. And then just flagging that predictive methods are based on what we've seen. What do we expect to see in the future? We're not going to talk about predictive methods today, but that's sort of like the next level of complexity. So descriptive statistics are really helpful. So, you know, you have a sample, but your sample might be like a few hundred or a few thousand people. And our human brains just cannot process raw data of that magnitude. So descriptive statistics help us interpret those raw data. It can be really hard for us to just on its face detect meaningful patterns, and that's where descriptive statistics come in handy. But you can't draw conclusions beyond the population that you studied. So you're really just limited to the sample and the people who you surveyed or who you collected data on. That's what you can do with descriptive statistics. You can describe them. Inferential statistics, so it's often impossible to study like everyone in a full population. So let's say you want to know something about like liver transplants in the US. It would be impossible probably to survey every single recipient of a transplanted liver in the United States. To do a full census of that population would be really hard. You might survey just a sample of liver transplant recipients, like in California or in the UCLA health system or something. So when you can't look at a full population and you have to look at a sample, this is when inferential statistics kick in. And basically the robustness of your inference depends on how well your sample represents the population. So there's always going to be some uncertainty and there's always going to be some bias, but you want to minimize those and have your sample represent the population you're interested in as closely as possible. So like you could be a sample of lots of different communities, right? You could be a sample of medical students at UCLA or graduate students at UCLA or just students at UCLA or people who live in LA, right? So these are kind of like zooming out what population you might be a sample of, or, humans at the highest level, right? And so you need to think about when you have a sample, like when I have you all as my sample, to what group here would I be comfortable inferring? In other words, for what population would you be a good sample? And my confidence in my inferential statistics is a function of that assumption. So like, I may not feel great about you all as the sample of people who live in LA for a variety of reasons, but like I might feel okay with you as an example of our sample of medical students at UCLA or people interested in global health at UCLA. So just thinking this through and thinking about the population that's truly of interest to you and then how well your sample that you have access to represents that population. A key part of inferential statistics is hypothesis testing. And if you've taken statistics class, hopefully you're not just having like terrible flashbacks now, but we are going to talk briefly about hypothesis testing. So in statistics and inferential statistics, there's something called a null hypothesis, which also is represented as this H0. And what the null hypothesis says is there's no difference between population A and population B on whatever it is that you're measuring. And the way that we test this is by comparing sample A to sample B. So the null hypothesis has to do with the population, but we're testing it by looking at our sample because we don't have access to that whole population. We're just looking at a sample of it. And your p-value is the probability essentially that the null hypothesis is true. So we'll talk more about p-values in a few slides. I just want to make a note here. So continuous data in particular exists in a distribution. A lot of the way that we structure our null hypothesis and set up our tests assumes that your data are distributed normally. This may or may not be the case, and you need to be careful about this. I didn't know where to put this warning, so I put it on this slide. But just thinking about whether your data are normally distributed will be important in thinking through sort of which inferential statistic you might undertake. Okay. We're going to come back to inference in a second, but I do want to cover descriptive data first, because this is sort of step one of conducting analyses. So if you have categorical variables, which almost definitely you will if you're doing surveys especially, you have options. So you can present frequencies of occurrence as either numbers or percentages. You can treat questions individually or you can combine them, and it really depends on your research question. And so I'm going to show you some data that we're actually collecting right now, and we can talk about sort of what you could do with the data that results from this. So we're doing a survey right now in Malawi about COVID vaccine, and one module has to do with where you've heard information about COVID vaccine. And so we go kind of source by source. And we ask, have you heard information from here? And if yes, what was the tone? Was it positive, neutral, negative, or you don't know? So we have like a lot. We have maybe like 15 or 20 sources of information in rows. And then we have these response options, kind of like a Likert, but not exactly. Okay. So what are some ways I can analyze these data? These data are like coming in now. So I'm actually facing this question right now. So give me some ideas you might have of how I could analyze these. You could say like a research question, for example, that I can answer with the survey data.
I guess if you were going to do an individual, then just like a very simple one could be like, what was the opinion, or what opinion did they get from the Ministry of Health? Just something like that. That's straightforward.
Mm-hmm. Great. So I could go item by item and say either, what's the distribution of answer, the distribution, have you heard or not? And if yes, what tone? I could say, for the Ministry of Health, what % of people said it was positive versus not, right? So I could go item by item, and even within there, I have options for, am I treating all these response options, or do I want to group them in some way? What are other research questions I could tackle here?
You could potentially break it up too into different like categories. I don't know, like one is media, so you have like newspaper, radio, television, and kind of compare like what's the different distribution of opinions on COVID vaccines between media and like practitioners, and compare the different categories.
Yeah, great. So I don't have to go row by row necessarily. I could think about grouping rows and talking about types of sources of information and whether that's positive or negative. How about grouping the columns or dropping columns? Can you imagine ways that I could sort of condense things that way? I have this collected at the individual levels. There's like 500 people who completed the survey, let's say.
I think very simply, you could just say, like, did they get an opinion of a COVID vaccine from this source? So just yes or no.
Mm-hmm. Yeah, so I could do that source by source. I could do that by groups, as you mentioned, or I could do it overall. How many different sources of information do people report on COVID vaccine, right? I could sort of just make this a simple dichotomous yes, no. I have options for how I treat those columns.
I was going to add, excuse me, one more really quickly.
Mm-hmm.
Looking at, you could ask like of the respondents who had heard information or opinions about COVID, what % were positive, neutral, or negative?
Yep, exactly. Yeah. So you guys, I think, picked up on probably all of these that I wrote. So like, what are the most frequent positive? Overall, are people hearing positive or negative? And then this one, so are different sources more likely to be positive or negative? How many different sources, right? So this is like mind-boggling when you get into it, because this is just one like module of this survey, but there are so many different research questions. And I think people tend to think of categorical variables as like a little limiting in your analysis, but I totally disagree. I mean, I think that your options here, you can collapse, you can combine, you really have lots of choices. And again, it comes down to really what your research question is for how you want to analyze the data. That's why specifying the stuff up front is really helpful. So when you have categorical variables, do not despair. You still have lots of options about how you want to treat things and how you want to analyze things. Most people really like working with continuous data. For as lovely as that survey module is, it is a somewhat limited set of response options, whereas continuous data, you have a much wider range of possible responses. So you just have many more options for dealing with it. If you have something that's a relatively small range that's discrete, like the number of pets that people have, you have options. You can treat that continuously, or you can treat it as a categorical variable. What % of people have 0 cats, and what % of people have 1 cat, and what % of people have 2 cats. I do want to say, like, treating things that are discrete and in a small range continuously is like a little tricky. I mean, like if you took an average of pet ownership, would 2.25 cats be like a meaningful value? And you'd have to think about that. And if you feel like that is not a meaningful value, then think about, each value as a response option of a categorical question. Let's say if you were looking at like number of, healthcare visits over the year, is a fractional visit meaningful to you? It might be, but it also might not be. And then you could think about treating things essentially like a categorical. There are plenty of examples where we take things that are discrete and a small range and we treat it as continuous. So like the total fertility rate. So 1.73 births per woman in the US is the fertility rate right now. You know, what's a 0.73 birth? But that's something we report as a continuous variable, even though it's discrete and a small range. Same with average household size, 2.53 people. I think if you're going to do this and you're going to treat things in a small range as continuous, one thing you do have to think about is like how many decimal points you want to report out. What's your kind of degree of confidence? Like, are you confident to the 10th place, to the 100th place? You know, if I told you the total fertility rate were 1.729156, you might be like, do you really know that to that degree of specificity? So I think especially when you're working with small range data, being really conscientious about the number of decimal places is important. Okay, with that being said, let's say you have continuous data and you're comfortable running kind of traditional descriptive statistics with it. Your first decision is thinking about whether you care about the middle of the distribution or the spread of the distribution. You can picture almost every continuous variable you can think of as existing in a distribution. It may be normal, it may not be normal, but no matter what, there's going to be low values, middle values, and high values. And so you have to think about, do you care about what's happening in the center, or do you care about kind of how fat that distribution is? If you care about the middle, then you're generally interested in things like the median, the mean, and the mode. I'm just going to flag that the mean is sensitive to the spread. So if you have a really long tail in one direction, it will pull the mean. So the mean is a bit funny because it tells you about the middle, but it's sensitive to the spread. The median is very strictly about the middle, and the mode is also very strictly about, you know, the sort of middle. If you care about the spread, then we're talking about range, variance, standard deviation, interquartile range. So there's various statistics. Generally speaking, people care about both and report a middle-based statistic and a spread-based statistic. So like they'll report the median and the standard deviation, both to give people a sense of what the center looks like, what's the sort of most common thing, what's the middle, and how sort of applicable is that? How fat is my distribution? So often you'll see a middle-based number and a spread-based number when people report descriptive statistics with continuous data. Once you get into inferential methods, this combines both categorical and continuous data here. There's lots and lots of options. That's where those flowcharts I showed you come in really handy. This is a super partial list, but it's probably like the most common things that you'll use. So t-tests are when we look at the difference between two averages, two means in continuous variables. Chi-square tests are when we have categorical variables and we want to see if like the percent of people with 0 cats versus 1 cat versus 2 cats is different among like women and men. That would be a chi-square test. So you're looking at differences between categorical variables. ANOVAs are looking at differences between 3 or more means. And then regression models are predicted relationships between variables. And I have a slide at the very end about just sort of breaking down regression models a bit. So this is like super partial list, but probably like, the top 4 methods that you will probably end up using a bunch in your research if you're doing inferential quantitative analysis. Okay, so we're going to walk through like a very simple, although it's not great, but it's simple example all the way from kind of research question on down. So let's say that my research question was, are people who attend medical school taller than people who do not attend medical school? You all don't know this because we're doing this over Zoom, but I'm quite tall. And so this question popped to mind quickly for me. So I'm interested in sort of the height of people in medical school versus the height of people who don't go to medical school. My null hypothesis would be medical students are the same height as people not in medical school. Okay, so my null hypothesis is there's no difference in height between my population of interest, medical students, versus a comparable population, people not in medical school. And this part in blue, we usually don't say out loud, but it is sort of the implied rest of this null hypothesis is based on the sample of first year DGSOM students who I've measured. So note here that my null hypothesis is about the population of medical students and the population of people not in medical school, but I'm exploring that on a sample of first-year students at this one medical school who I have access to their height data. So again, we usually don't say that part, but it is technically part of the null hypothesis here. And your alternative hypothesis, which is sometimes noted as HA for alternative, or sometimes as H1 as the flip side of H0, is medical students are taller than people not in medical school. Again, I don't say this part out loud, but based on my sample of first-year DGSOM students who I've measured. I want to note that in this case, I've written a one-sided hypothesis that medical students are taller than people not in medical school. I could have written a two-sided hypothesis, which would be medical students are a different height than people not in medical school. Could be taller, could be shorter. And actually, as you're setting up your statistical analyses, it matters whether you're interested in a one-sided or a two-sided relationship. So here I'm setting us up for a one-sided comparison. Are medical students taller than people not in medical school? So let's talk about descriptive statistics. So I could start with the mean and the median of the heights in the sample that I've measured. The mean will be very sensitive or likely to get pulled if some of your classmates are like super tall or some are super short. If you have both some super tall and some super short classmates, then the mean won't be as affected. But if like for some reason you have like one person in your class who's 7'7", then that mean is going to get yanked really far towards taller heights. So just being conscientious of how sensitive the mean is important. Okay, so I can describe you all or whoever I've sampled, but first year DGSOM students are just a sample of that population we're interested in. So we need to do some inference if we really want to address our research question. If I want to go beyond just painting a picture of the people I've looked at, I need to do some inferential statistics. So let's say that the average height of the first year students who I've measured is 71 inches. I might put a confidence interval around that. So this is one piece of inferential statistics that one could undertake. So let's say I ran analysis and I put a confidence interval of 68 to 74 inches. I just want to say in words like what that means. So what that means in a sentence is, I am 95% sure that the true average height of the population, so in this case, I am 95% sure that the true average height of medical students in the US, whatever the population you're looking at, lies between 68 and 74 inches. So this is really, I said earlier that like your confidence is a function of the level of inference you're making. Like, you know, am I 95% sure that the true average height of people in Los Angeles is 71 inches or 71 or lies between 68 and 74 inches, sorry, or is it that, you know, of medical students, of first year medical students? So this is where your relationship between your sample and your population come into play. Okay, so we're going to talk about confounding here again. So to really answer my research question, like, well, what I would need to do is I would have to look at the height of DGSOM students who I've measured, blah, blah, blah. And I would need to compare that to the height of similar people who aren't a DGSOM, actually who aren't in medical school at all, based on my research question. And to do this, I would want to avoid any mediators, confounders, et cetera. So I'm going to talk through a couple of scenarios that you might think through as you're doing this. So, all right. Let's just say that really tall people, this is not true for me, but maybe other tall people, were more likely to be recruited for varsity sports in high school and college. So they were less likely to take all the pre-med classes and do all the stuff it takes to get into really good medical schools. And so they're less likely to be in medical school. Is that a problem? And I would say, no, actually, that's okay. In this case, kind of participating in athletics is essentially sort of like a common cause. It's not a problem here. It is both related with sort of being tall and also going to medical school, but it's not confounding the relationship between the two. If, however, you hypothesize that this relationship was different for boys and girls, you would have to think about this as a moderator. And so this is sort of like worth thinking through, and if you need to measure it and kind of how you would need to measure it. I'm going to throw a confounder at you. I really struggled with coming up with a confounder here. And so, okay, it's not great, but just suspend disbelief for a second, okay? So maybe the California weather and our beautiful sunshine days is great for kids' growth, kind of like plants, right? And so kids who grew up in California are just like really tall because they're exposed to California sunshine and it's amazing. And also, if being a medical student here, if they're more likely to be from California, our relationship that we see between height and being in medical school here is confounded by growing up in California. Growing up in California is both affecting height and is affecting whether you're at this medical school. And so we think we're looking at a relationship between height and being in school here, but actually what we're looking at is growing up in California. So this is an example where you need to be really careful and think about how you're going to measure that confounder and how it's going to fit into your analysis. Okay. So you can see why kind of thinking this through and like, what are these variables? How do they relate is important for then finding a good comparison population and measuring all the right stuff when you're collecting these data. So a quick note back to p-values. So this slide and the next slide are really dense. And if you've already taken tons of stats classes, you can basically teach this better than I can probably, but we're just going to do like a quick pass through. So let's say we found this comparison group, we measured them, we measured the first year DGSOM students. Okay, we can do a t-test, in this case, a t-test of independent samples to compare the average height in sample A, our DGSOM students, to the average height in sample B, the comparison group. So we're conducting an inferential test of the average height in these two samples, and we're comparing the height in sample A to the height in sample B. Doing that will generate what's called a test statistic. In this case, because it's a t-test, it generates what's called a t-value. And that test statistic takes our sample average, which was 71 inches, and it compares that to the average in the other sample. Just as a reminder, the null hypothesis would say the average height in that other sample is also 71 inches. So the null hypothesis is that these are the same, okay? So if your t-value is big, that means there's a big difference in the averages in sample A and sample B. And when you have a big test statistic, you get a p-value on that test statistic that says, what is the probability that you would have obtained that test statistic if the null hypothesis were true? So if the null hypothesis were true, in this case, if both samples had an average height of 71 inches, we would expect a small test statistic because the difference is very small. And that's what the test statistic is reflecting. So the p-value is saying, what's the probability that that test statistic were obtained if the averages were the same? So if there's a huge difference in the heights, the test statistic will be huge, and there will be an extremely low probability that that would have been observed if the samples were the same, okay, or if the null hypothesis were true. So it's basically the test statistic and the relationship between the two samples as dictated by the null hypothesis generates the p-value, the all-important p-value that everyone is sort of holding their breath and waiting to see at the end of an analysis. Based on that p-value, we either reject or fail to reject the null hypothesis. Just noting here, we never accept the null hypothesis. We just reject or fail to reject it. So we're never 100% sure. There's basically always some error. So we never say that we're accepting the null, just reject or fail to reject. So in this case, let's say I ran these two averages, I get a t-statistic, and that t-statistic has a value, a p-value of 0.03. The sentence that would come out of my mouth would be, this is a long sentence, so I would never say it, but if I were to, so there is a 3% or less chance that the observed difference in average height between sample A, students here, and sample B, the comparison group, and the true population difference. Remember, we haven't seen the true population difference, but that's what we care about. So there's a 3% or less chance that what we saw in our samples and the true population difference would have occurred if medical students and other people are the same height, if the null hypothesis were true. So I think, you may have to like reread this slide and kind of re-listen to this a couple of times, but I think often people are a little floppy with kind of how they talk about the p-value and their acknowledgement of what the p-value is saying and what it has to do with the setup of the hypotheses and the test statistic that was run. So just kind of thinking this through and what p-values really mean, I think is really helpful. And then this is the last slide. It's also dense, I'm sorry. And then I'll stop, and I'm trying to leave room for questions at the end. So I just want to put in like a really quick plug for regression models, because you will come across them. It is inevitable. And I just wanted to sort of talk through what they are. So let's say you have two continuous variables. So here we have, this is information on cars. We have the weight of the car on our x-axis, and we have mileage, miles per gallon, on our y-axis. And we can see that there's an overall, just ignore the line, just look at the dots right now, overall a negative relationship, right? So weight goes up, mileage goes down. Okay, fine. But we might want to know, like, how much is that negative association? In other words, for each additional pound of weight, how much worse does mileage get? So you might be starting to have like flashbacks to high school math, because this is 100% what you learned in like algebra, or whenever you learned about geometry, whenever you learned about this stuff. So this is all regression models are doing. It is, regression models are fitting a line to these points and trying to minimize the vertical distance from the line to each point. So it's just trying to get a best fit line to your data set. And then it's basically telling you what the slope of that line is. So you probably recall from high school math that lines are expressed as y equals mx plus b. That is exactly what regression models are doing. So what they're saying is they give you an intercept. So like at 0 pounds, what would the mileage be? In this case, it would be 39.4. So that's your B in the y equals mx plus b world. And then it says for each additional unit of x, for each additional pound of weight, how much does that slope change? In this case, it goes down 0.006 miles per gallon. These last two lines are just showing you like literally what the notation for regression models are. So it's y equals alpha plus beta, that's the slope, times your x variable, in this case weight, plus an error term. And then the bottom line expands this for more variables. So you'd have beta 1, x1 plus beta 2, x2, and an error term. And it's important to know there's an error term. There's always an error term. You can see the line does not fit every point perfectly. So basically regression models are trying to minimize that error and get the best fit, but it's never perfect. So there's always going to be an error term in there. Okay. There are so many books out there. I mean, so many. I put 4 up here. The first one is the Rosner text, which is what actually I learned biostats on myself. One thing I really like about the Rosner text, I'm assuming the latest editions have it too, but the last like 6 pages maybe are all flowcharts, like the ones I showed you, but like way more detailed. And then it gives you the page numbers in the book to go back to see how to do that test. So I like that book a lot. The Van Emden Statistics for Terrified Biologists is really nice. It's like very plain language. Whelan's Naked Statistics, I assign in my data analytics class, actually. It's like written more like a nonfiction book, but it talks through like the intuition of statistics and thinking about numbers in this way. And then Coolidge has a book, Statistics, A Gentle Introduction, that's almost like between Rosner and Van Emden in terms of how technical or not the information is. If you start working in Stata and you need to know how to program all of this stuff, Stata has amazing help files for programming like everything I talked about. And then we have a terrific resource here at UCLA. IDRE is like an international resource, and it's kind of amazing that we have access to it here. So their website's really expansive, lots of FAQs, but then also they do consultations for those of us in the UCLA community. So you can go to them with specific questions and they can help advise about research designs and analysis, et cetera. So just wanted to give a quick shout out to IDRE. I use them all the time. They're amazing. Okay. Woo! Any questions about all of biostatistics?
I will say that was overwhelming even for me, and I'm a researcher, or I think I am. But I think one of the big take-home points that for you all to take away is just, you know, what you don't want to do is what I say, like go on a fishing expedition and like collect a bunch of data and then say, okay, what am I going to do with this data? That never goes well. And unfortunately, it's really easy to do that when you're, you know, kind of moving quickly. And, you know, it's just easy to say, I'll think about this later. So would really encourage all of you to go back to your mentors and really try to make sure that you've thought through your analysis plan, you know, you're thinking through how you're going to collect the data, how are you going to analyze the data, what questions are you answering, so that you don't end up on a fishing expedition.
Yeah, and I feel like the ice cream shark bite thing is just such a good example for like why thinking this through, like if you hadn't thought it through and you hadn't collected the data on warm weather, like you'd be stuck later. You'd be in this confounding situation with no data to get you out of it. And so that's why sort of thinking it through up front, specifying and then deciding how and what data to collect is really key. Are you all just shell-shocked with statistics knowledge? I mean, you can come back to me anytime and I may send you somewhere else to tell you the truth, but I mean, I'm always happy to sort of hear your questions and refer you onward to the right person to answer it if it's not me.
Great. Well, the survey link is in the chat. If people can take a couple minutes to do that. Ideally today, it should really just take a couple minutes, and I'll send it again in email with the slides and recording from this afternoon session. And as always, you can reach out to Corrina or to any of us with additional questions. We're around, like I said at the beginning, our next official session won't be until June, but do, stay connected and reach out whenever you want to.
Yeah, enjoy thinking about p-values and null hypotheses, et cetera, et cetera. If anyone has a better confounding variable for height, let me know. There was an example where if I had thought everything through at the get-go, I might have picked a different example, but I was like 4 slides in and I was like, oh no, I'm stuck with height. What's a confounder? So yet another argument for being cautious up front.
Thank you so much, Corrina.
Yeah, sure thing.
And
to everyone in June.
To all the students, I'm going to be reaching out to you just as a quick check-in to see how things are going with your planning for the research project. And if you need any help in navigating mentorship, things like that, I'll be reaching out in the next day. Bye.
Bye,
everybody.
Thanks, Corrina.
Thank you all.
Bye, everyone.
Bye.
Sure.